Hello everyone, thank you for your interest in our research. This presentation aims to give a summary of our article entitled Evaluation of Skid Steering Kinematic Models for Subarctic Environments. I am Dominic, and together with my co-authors, we are all part of NORLAB at Université Laval in Quebec, Canada. In order to introduce the article, I wanted to first talk about the project in which it takes part of. This project is called Self-Driving Optimized for Winter, or SNOW, and this project aims to adapt the autonomous navigation technologies to harsh winter environments, such as the ones that we have in Canada. For this project, we use a ClearPath Robotics Warthog UGV for experimental validation, and this UGV is equipped with the standard autonomous navigation sensor suite, which includes sensors such as LiDAR, IMU, camera, and GNSS antennas. Now, this article focuses mainly on motion modeling. Now, why is this important for autonomous navigation? If we take a look at the state-of-the-art approaches for three of the main components of the autonomous navigation pipeline, namely localization and mapping, path planning, and path following, we can see that each of them use a motion model to a certain extent. For example, for localization and mapping, the motion model can provide a good initial estimate of the vehicle displacement between time steps. Secondly, for path planning, it can allow to do path planning by taking into account information such as the vehicle limits or the energy consumption. And lastly, for path following, it can enable high-performance path following by using good knowledge of the vehicle behavior. We took a look in the literature and tried to find rovers that were deployed in winter conditions and that included some kind of autonomous navigation. We cited the 5 following articles. However, we found that no literature was focusing mainly on motion modeling for autonomous robots in snowy environments. Which brings us to our contributions. We took 5 kinematic models for skid steering mobile robots, or SSMRs, and we did an experimental investigation of each of them in order to first evaluate their fitness for a heavy platform, secondly, evaluate their performance on snow-covered terrain by using more than 2 kilometers of trajectories, and thirdly, highlight the impact of angular motion for the accuracy of such models. Now, why do we want to use kinematic modeling for skid steering mobile robots as opposed to dynamic modeling? In the literature, kinematic modeling tends to be more popular for 2 main reasons. The first one being that they are more robust to wrong parameter identification, and the second being that they do not require any knowledge about the inertial information of the robot's body, which is not always easy to find from the manufacturer. Now, what does a kinematic model aim to do? It aims to compute the time derivative of the robot states, which is the robot's velocity in the plane as well as its angular velocity, by using the knowledge about the wheel velocities on the left and right side of the body as inputs. The relation between both of them is given by the kinematic model J. In other words, the kinematic model provides an estimation of the kinematic states of the robot by using the left and right wheel velocities of the robot as inputs. The relation between both of them is given by a Jacobian matrix J, which includes a set of kinematic parameters that aim to model the vehicle behavior on different terrain types. Now, for the sake of simplicity, in our article, we highlighted the differences between each model only by expanding the Jacobian matrix J that is shown here. Now, in order to find the optimal set of K parameters to describe the behavior of the robot on different terrain types, we manually drove our platform in 2 separate environments, namely an underground parking lot and snow-covered terrain. Now, for both of these environments, we used the ICP algorithm in order to provide accurate ground truth localization of the robot's body. Now, this algorithm uses LiDAR measurements and provides a map of their environment, which is shown, a map for both environments is shown in the bottom 2 figures. Now, for both environments, what we did is we drove two separate trajectories, one being for the model training and another one being for model validation. Now, each trajectory was split into n number of segments, and the length of each segment corresponds to an horizon length, being called h. Now, the first thing we did is an analysis of the impact of such horizon length on the model performance, on the model accuracy, prediction accuracy, sorry. Now, in this figure, what we can see is on the x-axis for both sides is the length of the evaluation horizon, and on the y-axis on the left is the relative model prediction error when compared to the ground truth, and on the right is the interquartile range of the distribution of such errors. Now, what we can see in this figure is that models that are trained on smaller horizons tend to perform better on smaller evaluation horizons, and the opposite can be said for models that are trained on longer training horizons. What that means is that the training horizon of a model should be chosen according to the desired application of the model. Secondly, we compared the 4 trained kinematic models that are presented in this article. What we can see in this figure is on the left side, we can see the relative prediction error for translational displacement, and on the right side, we can see the same error but for angular displacement. The red distribution shows the errors for the robot when operating on concrete, and in blue we can see the errors when the robot is operating on snow-covered terrain. Now, what we can see in this figure is that the models perform similarly as good for both terrain types. However, we can see that for angular motion, we see a superior performance for the model being named the extended differential drive symmetric model. Finally, we compared the commanded angular displacement that was sent to the robot that we can see on the x-axis of this figure with the measured angular displacement of the robot's body that was given by the ICP algorithm that is shown on the y-axis of this figure. We can see the distributions for the the displacements for snow-covered terrains on blue in this figure, and we can see the distribution of displacement on concrete in red in this figure. The shaded areas represent the interquartile range of this distribution. Now, what we can see in this figure is that for commanded angular displacements of more than 30 degrees per meter, the actual measured displacement is bigger for snow-covered terrain, which means that turning is more efficient on snow-covered terrain. However, the behavior of the vehicle on snow-covered terrain adds some non-linearity that we can see here. Secondly, we can see that the interquartile range tends to be higher when the vehicle operates on concrete, which would lead to think that there is more uncertainty to model when modeling the behavior of the vehicle on concrete than on snow-covered terrain. Lastly, for future work, we aim to implement models that reason with the vehicle dynamics in order to improve model prediction performance. And also we aim to use such models in order to conduct path following that will be robust to harsh winter environments, which mainly includes high change in vehicle behavior. For example, if the vehicle operates one time on dry concrete and then moves on to deep snow. And secondly, that would be robust to the loss of the localization accuracy that could be caused by snowfall. And finally, this is all part of the bigger goal of the SNOW project, which is to improve autonomous navigation in snowy environments. Thank you for listening to my presentation. I hope you liked it, and if you want additional details, I hope you will read our article.